Hello, I'm Vivek Sharma. My registration number is 19 BCE 1043, and today I'm talking about AlphaGo with deep reinforcement learning. So the AlphaGo is developed by DeepMind, which is a agent used to play the game of Go. Now, first of all, let us try to understand why the game of the Go is hard. So, if you look at the board, there are hundred of different places that this stone can be placed down. As we know that in a Go we uses a stone. So, and there are hundred of different ways that white can respond to each one of those moves. Hundred of ways that black can respond to turn to white moves, and we get this enormous search tree with different types of hundreds of times of possibilities. Now, as we can see in other board game, we can have state spaces in some feasible manner or a fixed amount of state, and we can also do some exhaustive search there. But when we talk about the game of Go, it is not feasible because there would be the billions of state space. So, uh, search as we have already seen that exhaustive search is not possible there. So like, what are the solution then? The first thing is that we need to reduce the breadth and width of the game. So reducing the breadth of the game is like sampling actions from the policy, that is the probability distribution over possible moves, action in position of S. So here A defines action and S defines states. And reducing the depth of the game is just like truncating the search tree at state S and replacing the subtree below S by an approximate value of Vs, which is just the optimal value of V star S that predicts the outcome from state S. So this the way we'll be reducing the depth with value network and reducing the breadth with the policy network. Now, what is AlphaGo? So AlphaGo is just a combination of supervised learning of policy network, reinforcement learning of policy network, reinforcement learning of value network, and Monte Carlo tree search. So talking about its total training. So first we train a supervised learning policy network directly from expert human moves, and then it provides fast, efficient learning updates with immediate feedback and high quality gradients. Then also we train it with the fast policy that can rapidly sample actions during rollouts. Next, we train a reinforcement policy learning network that improves the SL policy network by optimizing the final outcome of game of self play. And then this adjusts the policy towards the correct goal of winning games rather than maximizing predictive accuracy. And then finally, we train a value network that predicts the winner of game placed by the RL policy network against itself. Then AlphaGo efficiently combine the policy and value network with MCTS. So this is the training pipeline. Here we have seen that how the human expert positions are get learned with the help of supervised learning, which is a policy network, and then we send it for the reinforcement learning policy network, and it plays a lot of game with itself, and the value network gets created. So talking about supervised learning of policy network, so like to train the learning policy network, AlphaGo collect move for nearly 30 million board positions. Then it applies the back propagation in deep learning to train the model parameters like sigma. And then AlphaGo basically uses 50 GPUs to train the network, and it takes 3 weeks. The SL policy network achieves a 57% of accuracy, and it may sound not too accurate, but this policy network can beat an advanced amateur already. And then the reinforcement learning of policy network. Now we have a policy network approximate the master moves, but it is not accurate enough to beat a master yet. So in the second stage of training, AlphaGo starts playing game with itself to formulate better policy. First, we duplicate SL policy network and call it RL policy network. We use the policy gradient reinforcement learning to improve RL policy network iteratively. We start playing games using the new RL policy network then. And for our opponent, we randomly reuse one of the older RL policy network. We don't play each other with the same policy network because it will overfit the current policy. That is, it will memorize the moves rather than generalizing it for different opponents. So we play until the game is finished. For time step t, the game result zt is equals to 1. So if you win at the end, or minus 1 if you lose. So we modify the model parameter p to make the RL policy easier to win. So in fact, this is almost the same as the deep learning backpropagation, except we use the game result Z to determine which direction to move. Now the RL policy network takes about 1 day to train with the 50 GPUs. When we have reinforcement learning of value network. Now the result of a Go game can vary with a small chance. A small inaccuracy in the RL policy network can change a win to a loss. Now a human prioritizes the searches for moves and evaluates a board position accordingly. So in the last stage of AlphaGo training, we want to duplicate the human capability in evaluating a board position. We train a deep network to estimate the value of our position. In Go, the value equals 1 if we win or minus 1 if we lose. Later, we complement our policy network and value network with each other to search and to make better moves. Now we have something called MCTS or Monte Carlo tree search. So basically simulating moves suggested by the policy and the value network is the best way to find the next move. We simulate games starting from the current board position. We searches for moves and play simulated games until the end. Now if we play enough games, we will get an idea which moves likely get the most wins. In the process, we build a search tree recording sequences of moves we simulated and how many wins for each move. But the search space for Go is too large. We need to prioritize it so we can find the best moves in fewer games. Luckily, we get great advice from the policy and the value network. We use both information to provide our searches. But that is not enough. We should explore moves that we know little in our simulation so far, which we call exploration. Maybe the advice is off, so this help us to verify moves better. On the other hand, if we win a simulated game, we want to try the corresponding moves more often. So hence our search priority depends on like prediction from the policy network, prediction from the value network, how many times we pick the move, and simulated game results with wins. So the Monte Carlo search tree is the algorithm we use to prioritize and build this search tree. So this is the tree structure that we use. So basically MCTS encodes the game state and its potential move into a tree. Then each node in the tree represents a potential game state with the root node representing the current state. Each edge represents a legal move that can be made from one game state to another. Then at the start of the game of tic-tac-toe, the root node may have the 9 children, one for each possible move. Now each following child can only have one less child than its parent, since the previous moves are no longer available as options. So as we have already talked about MCTS, so it is the most basic way to play the to use playouts is to apply the same number of playouts after each legal move of the current player, then choosing the move which leads to the most victories. So now each round of the Monte Carlo search tree consists of 4 steps. First selection, then expansion, simulation, and then backpropagation. Now talking about simulation, so MCTS simulates many games to find out how good are the moves. The purpose of the selection step is to prioritize moves for further simulation. Now if our priority is correct, we can play fewer games to pick up better move. And then we have expansion. So like our search tree starts with the any current position. Then we add more positions into the tree reflecting what move, which is edges we have tried. Whenever we expand the tree, we initialize new edges. Edges are just like the state and action pairs, with probability indicating how good the move is. It is initiated by the SL policy network and will not be the updated anymore. Now, so it is used in the exploration in computing U. Like one can ask, why is it so initiated by the RL policy network? It turns out we want to explore more diversified moves. So the top moves in RL policy network are good, but less diversified. So SL policy network is learned from human experience. It turns out human tries more diverse option in exploring moves. And then we have simulation. So during this step, we roll out one or multiple simulation with the reward accumulated for each simulation. So like rolling out policies normally simply even more random, such as it is fast to execute. For example, a win might induce reward of +1 or a draw for 0 and a loss for 1. So and then another is the back propagation. Now this is the value newly added has been determined. Now the rest of the tree must be updated. So starting at the new node, the algorithm traverses back to the root node. During the traversal, the number of simulations stored in each node is incremented, and if the new node simulation resulted in a win, then the number of win is also incremented. So here we can see the MCTS in AlphaGo, and utilizing all the four steps of selection, expansion, evaluation of backup. Backup is just another name of backpropagation. Thank you.